All right, so today we are going to be taking a deep dive into something pretty amazing.
Yeah.
The Future Circular Collider.
The FCC.
The FCC.
That's right.
People have been sending in a ton of articles about it, so
yeah.
I think it's time to, really dive deep.
It's time to unpack it.
And figure out what this is all about.
Yeah, so the Future Circular Collider, it's basically the next generation of particle accelerators.
Right.
It's taking it to a whole nother level.
Next level.
We're talking about a machine potentially bigger than anything that has ever been built before.
I mean, are we talking like bigger than the Large Hadron Collider?
Oh, yeah, much bigger. We're talking like multiple times bigger.
Okay, so
it's really...
Before we get too far into like the scale of this thing,
sure,
can we talk about like what are the big questions? Like, why are we even, thinking about building something like this?
I mean, the big questions are the big questions of the universe, right? Like, are there particles we haven't discovered yet?
Okay.
What secrets can the Higgs boson unlock?
Right.
Can we find evidence of dark matter?
Okay, so this is really...
These are...
about
this is the cutting edge of physics.
The cutting edge.
Right here.
All right, so we've got these big questions.
Yeah.
But why do we need another collider? Like, we already have the Large Hadron Collider.
We do.
That was a pretty big deal.
Yeah, and it was an amazing machine, we learned so much from the Large Hadron Collider.
Yeah.
But, it definitely has limitations.
Okay.
And so the FCC is all about pushing further into the unknown, higher energies, more precision, to unravel these mysteries that are beyond the standard model of particle physics, which we've talked about before.
Right, yeah. And so it's kind of like saying the LHC was great.
Yeah.
It was
amazing.
Amazing, but now we need to go further.
We need the next step, the next level.
So to understand, like, how we got to this point of, needing to build this massive new collider.
Right.
Can you give us, like, a quick history lesson? But, like, make it fun.
I'll try to make it fun.
Okay.
So early days of particle physics, back to the 1930s, scientists start with these relatively small machines called cyclotrons.
Like, how small are we talking?
Like room-sized, not huge, but they were basically circular chambers with magnetic fields that accelerated particles in a spiral path.
So it's like a
tiny racetrack for particles.
Tiny racetrack. Okay, I like that.
Yeah.
Okay, so we've got these tiny racetracks.
Yeah.
What happens next?
So then as technology advanced, we're not sticking with those tiny racetracks forever. Scientists developed more powerful accelerators called synchrotrons.
Okay.
And these machines use a combination of electric and magnetic fields to accelerate particles to much higher energies. We're talking about places like Brookhaven National Lab in the U.S., Fermilab also in the U.S., and of course CERN in Europe.
Right, and CERN is where we have...
That's right.
The Large Hadron Collider.
The LHC.
Which, famously discovered the Higgs boson.
Made history.
Right.
Absolutely, yeah.
Right.
I mean, the Higgs boson was like a missing piece in the standard model of particle physics, which, we talk about it a lot. It's basically our best description of how the universe works at the smallest level.
Right.
You can think of it like the periodic table, but for fundamental particles and forces.
Okay.
And, discovering the Higgs was this huge triumph.
Yeah.
But it also raised a lot of new questions.
It always does, doesn't it? It's like you answer one question and then suddenly you have...
That's science.
10 more.
Exactly.
So,
and to answer those questions, we need to go further.
Okay.
We need to push further.
So enter the Future Circular Collider?
The Future Circular Collider.
Yes. Okay.
So
what makes this so different from the LHC?
So, I mean, the sheer scale of it is mind-boggling, right? We're talking about a tunnel with a circumference of up to 100 kilometers.
It's 100 kilometers.
Which is
enormous.
Multiple times bigger than the LHC's 27 kilometers.
Yeah.
So, I mean...
We're talking about a tunnel that can fit several cities inside.
Yeah.
Like, why does it need to be so big?
It all comes down to energy, right? The larger the circular path, the more energy we can pack into these particles before smashing them together.
So bigger track?
Bigger track.
Faster race cars?
Faster race cars, more spectacular crashes when they come.
More spectacular crashes.
Yes.
All right, I'm with you.
And so what happens in those crashes?
Yeah, what are we looking for?
We are looking for...
In those crashes?
The unknown, basically.
Okay.
So when those particles collide at such high energies, they can create this whole shower of new particles.
Okay.
And some of which might be the exotic ones we're hoping to find. Things like supersymmetric particles.
Supersymmetric particles.
Yeah, so...
Break that down for me.
You see, the standard model, right?
Right.
It's incredibly successful.
Yes.
But it doesn't explain everything.
Right.
It doesn't explain why gravity is so weak compared to the other forces or what dark matter is made of.
Right.
And supersymmetry, or SUSY for short, offers this possible solution.
Okay.
It predicts that for every known particle, there's this superpartner particle.
A superpartner, all right.
It's like, imagine the universe having this secret twin with this whole set of particles we haven't discovered yet.
That would be pretty mind-blowing.
It would be revolutionary.
If we discovered that.
Yeah.
But what if we build this giant collider, spend all this money, do all this, like, amazing engineering work, and we don't find anything?
That is a possibility.
Okay.
It's a possibility that we don't find anything new at these higher energies, and that would mean that, well, maybe the standard model is essentially complete.
Like we've reached the end.
We've kind of figured it all out, but
the row.
It's more likely that we'll find something that completely rewrites our understanding of the universe.
So it's kind of...
Every time we push the energy frontier in particle physics...
It's a gamble.
It's a gamble, but it's a good gamble.
Okay.
We've uncovered something new and unexpected.
All right, so I'm starting to see why physicists are so excited about
they're very excited.
But it's not just one giant collider, right? It's like a multi-stage project.
You're right. The FCC is designed as a staged project.
Okay.
Meaning it will be built in phases.
Okay.
Each with different goals.
Tell me about these phases.
All right, so the first stage is called the FCCE, which stands for electron-positron collider.
Okay.
It's designed to study the known particles, like the Higgs boson, with incredible precision. So think of it as like a fine-tuning stage where we're really zooming in on the particles we already know and looking for these subtle deviations from the standard model.
So precision is key for this.
Precision is key, yeah.
What about the next stage?
All right, so the next stage, if it gets approved, is the FCC, which stands for proton collider.
Okay.
And this is the one that really pushes into that high energy frontier with collision energies of up to 100 TeV.
Hold on, TeV. Can we explain that?
Of course. So TeV stands like tera electron volt.
Okay.
Which is a unit of energy.
Okay.
And it's a massive amount of energy concentrated in a tiny space.
Like how?
I mean, imagine the energy of a mosquito flying at 60 miles per hour.
Okay, I can imagine that.
Right, that's about a trillionth of a TeV.
Okay.
Now, pack that minuscule amount of energy into a space billions of times smaller.
Okay.
And you start to get an idea of the power of the FCC.
Okay, so a lot of energy.
A lot of
energy. Packed into a very small space.
Yeah.
Okay. What kinds of things can we discover with that much energy?
Well, I mean, this is where it gets exciting, right? With the FCCH, we would be entering uncharted territory, potentially creating particles much heavier than anything we've ever seen before.
Wow.
It's possible we could even create dark matter particles directly in the lab.
Create dark matter?
Yeah, I mean, it's a possibility.
I mean, I can only imagine the level of engineering.
Oh, it's incredible.
And technology that would be needed.
Oh, yeah. Pushing the limits of technology in so many ways.
To build a machine like this.
I mean, we need to build super powerful magnets, super cool the entire system, manage incredibly intense beams of protons.
It's like building a super fast spaceship.
It is, except instead of launching into space, we're launching into the subatomic world.
Okay, before we get too carried away with like all the cool stuff we might find. Let's talk about why this project matters.
Sure.
I mean, it sounds incredibly complex.
It is.
And expensive. Are we sure this is even possible?
Well, scientists and policymakers around the world are definitely considering these questions very carefully.
Right.
But I think the potential rewards far outweigh the risks. You know, I mean, remember, fundamental research often leads to these unexpected breakthroughs that benefit society in countless ways.
Can you give me some examples?
Like, think about the World Wide Web, which was born at CERN as a way for physicists to share data.
Right.
The technologies we develop for the FCC, things like advanced computing and superconductors, will likely have applications in medicine, energy, countless other fields.
Okay, so it's
really an investment.
An investment in the future.
Yeah.
And the things we learn along the way
absolutely
could have impacts that we can't even imagine yet.
We can't even imagine yet.
Okay, so this has been an incredible overview of the FCC.
Yeah.
And I'm already hooked.
Good.
We've talked about, how we got to this point.
Yeah, evolution, yeah.
The evolution of particle accelerators.
Yeah.
The incredible scale of this thing.
Yeah.
And the potential for, like, groundbreaking discoveries.
It's groundbreaking.
But there's another stage to this project, right?
Yes, there is.
We haven't even talked about...
We haven't talked about the FCC heat.
The FCC heat?
That's right.
What's that all about?
Well, FCC combines electrons and protons, and it's kind of like having two different kinds of microscopes to study the same object.
Okay.
So allows us to study the proton's structure in detail.
Okay.
And test our understanding of quantum chromodynamics, which is the theory of the strong force that holds quarks together.
So it adds like a whole new layer.
A whole new layer, yeah.
Complexity and potential for discovery.
Exactly.
To this already very complex project.
It really highlights the modular approach of the FCC, right? By building this massive tunnel,
right.
We're creating this platform for decades of research and discovery across these different areas of particle physics.
All right, so that's where we're going to pause for now.
All right.
I'm already buzzing with all these exciting possibilities.
Well, we've got more to come.
Yeah, I know.
We'll be back soon to delve even deeper into the future circular collider.
Can't wait.
All right.
All right.
Welcome back to our deep dive into the future circular collider.
I'm ready to go even deeper. Last time we talked about the FCC's potential for uncovering new particles and stuff.
Yeah.
You also mentioned something about testing the standard model with incredible precision.
Right, right.
How does that work?
So one way to do that is by studying something called lepton universality.
Lepton universality.
Yeah, it's a mouthful, but basically the standard model predicts that electrons, muons, and tow particles, which are all types of leptons, should behave identically under the weak force.
Okay.
But by studying the decays of the W and Z bosons with incredible precision at the FCCE,
right,
we might find tiny deviations from this prediction.
So we're basically looking for cracks in the foundation of the standard model.
Exactly. We're looking for, those little hints that there's something more going on, something beyond what we currently understand.
Okay, that's exciting.
And the FCCE will also allow us to measure the Higgs boson's interactions with other particles with incredible accuracy.
Okay.
This will give us a much clearer picture of the Higgs field, which is responsible for giving particles their mass.
Right. And I remember from our last deep dive, you were describing the Higgs field as this invisible energy field.
Yes.
That permeates all of space.
It's everywhere.
And it's mind-boggling to think that something we can't see or touch could be responsible for something as fundamental as mass.
It really is. It's one of those things that makes you really step back and just kind of awe at the universe.
Yeah. And
Higgs boson is like this ripple in that field, a way for us to actually study its properties.
Okay.
And the more precisely we can measure the Higgs boson's interactions,
right,
the better we can understand the Higgs field and its role in the universe.
So it's not just about finding new particles.
No.
It's also about refining our understanding.
Refining.
Of the ones we already know.
Absolutely.
Okay, so we got FCCE focusing on precision measurements.
Yes.
Of known particles.
That's right.
Then we have FCC-HH, which is all about pushing into that high-energy frontier.
Push it to the limit.
And potentially discovering new particles like those supersymmetric particles we talked about.
Yeah, supersymmetry, that would be amazing.
But what are some other exotic particles that might show up at the FCC?
Ooh, well, one possibility is extra gauge bosons, which are particles that mediate forces.
Okay, remind me, what are gauge bosons?
So the standard model already includes force-carrying particles like photons, which mediate the electromagnetic force, and gluons, which mediate the strong force.
Right.
But some theories predict the existence of additional gauge bosons, which could point to new forces of nature that we don't even know about yet.
Wow, so it's like discovering a whole new set of rules.
A whole new set of rules governing the universe.
Governing the universe, okay.
It would be a completely new chapter in the physics textbook.
Okay, what else?
Another possibility is finding composite Higgs partners.
Composite Higgs partners, what are those?
So the standard model treats the Higgs boson as a fundamental particle, meaning it's not made up of any smaller components.
Okay.
But some theories suggest that the Higgs boson might actually be composite, made up of even smaller particles.
So it's like finding out that an atom,
yes,
which we thought was this indivisible thing,
exactly,
is actually made up of protons, neutrons, and electrons.
Exactly.
And then finding out that those things are made up of even smaller particles.
It's like those Russian nesting dolls.
Okay.
Keep opening them up and finding smaller and smaller things.
Okay.
And so if we find composite Higgs partners, it would be a major paradigm shift in our understanding of the Higgs boson and its role in the universe.
Okay. So lots of cool stuff we might find.
Lots of cool stuff.
But I think, one thing that everyone's really curious about is dark matter.
Dark matter, yes.
Is there any chance the FCC could help us solve that mystery?
That is the billion-dollar question, isn't it?
Yeah.
I mean, we know dark matter exists because of its gravitational effects on galaxies and stuff.
Right.
But we have no idea what it's made of. It's like this invisible scaffolding holding the universe together, but we're completely in the dark about its true nature.
It's both fascinating and frustrating.
Oh, absolutely.
That we know it's there,
Yeah.
but we have no idea what it is.
Exactly.
How could the FCC help?
So the leading theory is that dark matter is made up of these things called weakly interacting massive particles, or WIMPs for short.
WIMPs, okay.
And if WIMPs exist within a certain mass range,
okay,
the FCCH might be able to produce them directly.
Wait, we could actually create dark matter in the lab?
I mean, it's a possibility, right? It's one of the things that really gets people excited about the FCC, even if we don't create dark matter particles directly.
Right.
The FCC could provide crucial insights that help us narrow down the search.
Sure.
Like, we might see evidence of dark matter interacting with other particles, or we might discover new particles that suggest a particular model of dark matter.
So we're not guaranteed to solve the dark matter mystery.
It's not a guarantee, no.
But the FCC could give us some good clues.
Oh, absolutely.
To help us figure it out.
It could give us those missing pieces of the puzzle, those hints that we need to really crack this thing wide open.
And that's the beauty of fundamental research, right?
That's the beauty of it.
It's like you're pushing into the unknown.
Yeah.
You don't necessarily know what you're going to find.
You never know what you're going to find.
But you're guaranteed to find something.
You're going to learn something new, that's for sure.
Okay, well said.
But before we get too carried away with all these potential discoveries, I think we need to take a step back and talk about how this massive machine actually works.
Okay.
Like, how do we get those particles up to those incredible speeds? How do we even detect them?
Yeah, how does this thing actually work?
Right, because it's all very well and good talking about these exotic particles and new forces and all that.
Right.
But we need to actually have a machine that can do that.
Yeah, it's not all just theory.
Exactly. So it's a blend of cutting-edge technology
Right.
and scientific ingenuity.
Okay, so let's break it down.
All right.
Starting with the basics.
So let's imagine we're working with the FCC-H, the proton-proton collider.
Okay, proton-proton. All right.
So we need a source of protons,
right,
which we get by stripping electrons from hydrogen atoms.
Okay, simple enough.
Simple enough, yeah.
So we've got our protons.
We've got our protons.
So how do we get them moving?
So that's where these things called radio frequency cavities come in.
Radio frequency cavities.
Yeah,
okay.
so these are special chambers that use electromagnetic fields to give the protons little kicks of energy, pushing them faster and faster along the circular path of the collider.
So it's like a series of boosters.
Like boosters.
Propelling these protons.
Yeah, exactly.
To near the speed of light.
Near the speed of light, that's right.
Okay, and then how do we keep them moving in a circle?
To keep them moving in a circle, we use these incredibly powerful superconducting magnets.
Right.
And these magnets bend the proton's path, forcing them to follow the curve of the collider ring.
Okay, so we've got these protons.
Whizzing around.
Whizzing around the tunnel.
Yeah.
At incredible speeds.
Yeah, at fantastic speeds.
But how do we make them collide?
So at specific points along the ring,
okay,
we have these things called interaction points.
Interaction points, okay.
Where the beams of protons traveling in opposite directions are focused and steered to intersect.
Okay, so that's where the magic happens.
That's where the fireworks happen.
What happens when those protons collide?
When those protons smash together at such high energies, it's like this subatomic fireworks show.
Okay.
A whole shower of new particles is created.
Right.
And some of which might be the exotic ones we're hoping to find.
Okay, but how do we see them? They're incredibly tiny, right?
They are incredibly tiny.
And short-lived.
That's where the detectors come in?
The detectors.
These are massive, multi-layered instruments.
I've seen pictures of those detectors.
Oh, they're incredible, aren't they?
They look like something out of a science fiction movie.
They really do. Each layer of the detector is designed to measure different properties of the particles, like their charge, momentum, and energy.
So it's like piecing together a puzzle.
Exactly.
Using all these different measurements.
Right.
To reconstruct what happened in the collision.
And this is where things get really challenging, because the rate of collisions in a high luminosity machine like the FCC is enormous.
Like, how many are we talking?
Billions of collisions per second.
Billions. Okay, so that's a lot of data.
That's a lot of data.
How do we even begin to, like, sift through all that information?
So that's where advanced computing comes in.
Okay.
We use these sophisticated algorithms and machine learning techniques to analyze the data,
right,
identifying the rare events that might signal new physics.
So like looking for a needle in a haystack.
It is a needle in a haystack situation.
But the haystack is enormous.
It's a very large haystack.
Okay, so that's how we we detect the particles.
Take how we detect them.
But all this incredible technology, this massive scale, it has to come with some serious engineering challenges.
Oh, it definitely does.
I mean, building a 100-kilometer tunnel sounds like a massive feat in itself.
It's a huge undertaking.
What are some of the other engineering hurdles that, you have to overcome?
So many.
Welcome back. Last time we were talking about all the engineering challenges in actually building the FCC.
Yeah, building a machine this complex and powerful, I mean, it's a massive endeavor.
Right.
Pushing the limits of engineering and technology on so many fronts.
Yeah.
Even just constructing that 100-kilometer tunnel, that's a massive undertaking in itself.
Yeah.
We're talking about burrowing through miles of rock, navigating different geological formations, making sure that tunnel is stable and safe for decades to come.
So like a mega engineering project.
Oh, yeah.
On par with building the world's longest bridges or digging the deepest tunnels.
Absolutely, yeah.
Wow.
And then, on top of that, remember those superconducting magnets we talked about earlier?
Oh, yeah, those are vital.
Those are essential for guiding the protons around the ring.
Right.
They have to be incredibly powerful, I mean, to keep those protons on track at such high energies.
Right.
We're talking about magnetic fields several times stronger than the ones used in the LHC.
Wow.
And to keep those fields stable, the magnets need to be super cooled to almost absolute zero, using liquid helium.
So we're essentially talking about creating the coldest place on Earth.
Pretty much.
But inside a massive tunnel.
Yeah, it's quite the engineering challenge.
That's incredible.
And then there's the challenge of managing the beams of protons.
Oh, right. Yeah, those incredibly energetic beams.
These beams carry an incredible amount of energy.
Yeah.
And even the slightest instability can have catastrophic consequences.
Right.
So we need sophisticated feedback systems to constantly monitor and adjust those beams, keeping them focused and stable.
So it's kind of like, what, juggling chainsaws while riding a unicycle on a tightrope?
Something like that, yeah.
I'm starting to get a sense of just how much work goes into a project like this.
Oh, yeah, it's a truly collaborative effort.
Yeah.
Physicists, engineers, computer scientists, geologists, and countless others, all working together to make this dream a reality.
It's like a global scientific orchestra.
It really is.
Everyone playing their part to create something truly harmonious.
Beautiful.
But all of this comes at a cost, right?
It does.
We've touched on this before, but I think we need to address the elephant in the room.
Yeah.
This project is estimated to cost tens of billions of dollars. Can we really justify spending that kind of money on something that seems so abstract, so far removed from our daily lives?
That's a fair question. It's one that deserves careful consideration. But I would argue that the potential rewards far outweigh the costs. First of all, remember, this funding would be spread out over decades.
Right.
It's not like we're writing one giant check tomorrow.
Right.
And it's not just about the money. It's about investment, an investment in our future.
So it's not just about the discoveries we make, but also about the knowledge and expertise we gain along the way.
Absolutely, yeah.
Right.
The technologies developed for the FCC, things like those superconducting magnets and advanced computing systems, they have applications in countless other fields.
Right.
Including medicine, energy, and more.
So it's like planting seeds.
Yeah.
That will bear fruit for generations to come.
That's a great way to put it.
And the scientists and engineers trained on this project will go on to make contributions in all sorts of fields.
Absolutely.
It's about creating a ripple effect of knowledge and innovation.
That's what it's all about.
And let's not forget about the intangible benefits, like the inspiration and wonder that a project like the FCC can spark in young minds.
I love that, yeah.
Imagine a generation of students inspired to pursue careers in STEM fields, fueled by the dream of unlocking the secrets of the universe.
It's a beautiful thought.
It's about pushing the boundaries of human ingenuity and imagination, showing what's possible when we dare to dream big.
I completely agree.
So in the end, the FCC is more than just a giant machine, isn't it?
It's so much more.
Yeah.
It's a testament to human curiosity, a catalyst for innovation, and a symbol of international cooperation.
It has the potential to change the world.
Absolutely.
Not just through groundbreaking discoveries,
Yeah.
but through the ripple effects of knowledge, technology, and inspiration.
It's about understanding the universe at the most fundamental level.
Yeah, the very building blocks of reality.
Exactly.
Okay, I think you've convinced me. As we wrap up our deep dive into the Future Circular Collider, I'm left with a sense of awe and excitement.
I am too.
The future of science is bright, and the FCC is poised to be a shining beacon, leading us into uncharted territories of knowledge and discovery.
It's going to be an incredible journey.
So let's embrace that sense of wonder, Let's support the scientists and engineers who are working tirelessly to make this dream a reality.
They're doing amazing work.
And let's prepare ourselves for the incredible journey ahead.
Yes.
Because who knows what we might find when we dare to explore the unknown. This has been The Deep Dive, a journey to the cutting edge of science and technology. Thanks for joining us.
Thank you.